In this video, we're looking at the differences between linear motion and rotational motion. Specifically, first we're looking at the differences between what is rotation and what is a revolution. Although a lot of times we use these terms interchangeably, there is a little bit of a difference between the two. In order to understand the difference, we first need to understand what we mean by the term axis. An axis is the straight line around which rotation takes place. If we look at the example here of the hamster wheel, we see that the axle, or the axis, is right in the middle of the wheel. It is the point at which everything else rotates about. Now, the differences between rotation and revolution are all about where the axis is located. If a rotation is occurring, that means that the object turns about an internal axis, or when an axis is located within the body of the object. For example, the wheel itself is rotating because the axis actually goes through the wheel. A revolution is when an object turns about an external axis. For example, the hamster is revolving because the axis does not go through the hamster. Some examples of things that both revolve and rotate are a Ferris wheel and the Earth. Let's first look at a Ferris wheel. So a Ferris wheel both undergoes the types of rotational motion of rotating and revolving. The Ferris wheel itself is rotating because the axis goes through the Ferris wheel. However, the riders on the Ferris wheel are revolving because the axis is not going through the people on the Ferris wheel. Another example of something that undergoes both types of rotational motion is the Earth. The Earth rotates about its axis once every 24 hours. So the axis of the Earth would be right here. It goes through the center of the Earth. And so the Earth rotates about this axis once every 24 hours, and that's how we get night and day. However, the Earth also revolves around the Sun. So the Sun is off in the distance, and the Earth is going around the Sun once every 365 days, and that's how we get a year. So in this situation, the axis is at the Sun, and it's not going through the Earth. Now, on your worksheet here, on your note packet, I want you to determine if the examples given are examples of rotations or revolutions. And in order to do so, I want you to pause the video and answer the questions. And then once you're ready, unpause, and we'll go over the answers. So at this point, please pause the video and go over or answer your questions A through F. All right, welcome back. Let's go through them one by one. The first example, it says, David is sitting on the outside edge of a merry-go-round. So a merry-go-round here, like you might see at the park, and David might be one of the boys here on the outside. Notice that the axis, if this is David right here, the axis is not going through David. And so therefore, this is an example of revolving, because the axis does not go through the person moving in a circle. The next one, it says, Susan is spinning around like a ballerina. Now, if we look at the axis here, the axis is actually going through Susan. And so therefore, this is an example of rotating. If the axis goes through the object moving in a circle, then it's an example of rotating. Letter C, it says, Jane is swinging a ball attached to a rope around in a circle. The axis in this situation is right here, where the person's hand is, and the ball is not going through the axis. Therefore, this is an example of revolving. Next example says, a mound of clay is spinning on a potter's wheel, and the clay is in the center of the wheel. Here our axis is right here, going through the center of the clay. So therefore, it is an example of rotating since the axis goes through it. The last two, it says a turntable, which is a record, is spinning with a ladybug sitting on the outer edge. This would be ladybug B. It first asks, what is the turntable doing? And we see that the axis actually goes through the turntable. So therefore, the turntable is rotating. However, the axis does not go through the ladybug. And therefore, in letter F, it asks, what is the ladybug doing? Well, the ladybug is revolving because the axis is not going through the ladybug. The next thing we want to look at is how are linear speed and rotational speed different? Well, first we want to define linear speed. And linear speed is the distance traveled per unit time. It is how fast an object is moving. Now, as you get further from the axis of rotation, your linear speed will increase. To demonstrate this, I have a short clip of some students doing the whip. You may have done this before if you've ever been ice skating. A lot of times it's done while ice skating. And the students are joining hands and they're going to move, trying to stay in the same line as they move in a circle. We see that the person on the outside has to move a lot faster than the person on the inside. So the further away you get, the faster linear speed you have to travel. Now, a lot of times we call this linear speed tangential speed. We call that because of the direction of the motion. If we look at the person on the outside of that whip, that person is moving forward. And we see that this line, this arrow here, we say is tangent to the circle because it makes a 90-degree angle with the radius. It is essentially just touching that circle at one point. So another name for the linear speed is tangential speed because the direction of the motion is always tangent to the circle. Even when the student is over here, they are moving forward. And again, that is tangent to the circle. It makes a 90-degree angle with the radius. Now, another type of speed we can talk about is the rotational speed. This is the number of rotations per unit of time. It is essentially how fast an object is spinning. Now, unlike linear speed, all parts of a spinning object have the same rotational speed. They go through the same angle in the same amount of time. Another name for rotational speed is angular speed, because we're talking about how fast the angle is changing. To show that the linear speed and angular speed are going to be different from one another, here we have our record, or turntable, and we see that all parts of the turntable rotate at the same rotational speed. So the rotational speed is the same, because they go through the same angle the same amount of time. For example, if we look at this point here, which I'll call point A, and this point here, which I'll call point B. Now, they would both go through an angle of 360 degrees if we were to continue this out. They would go through the same angle of 360 degrees, and they would do so in the same amount of time. So if we had two objects sitting on this record here, this turntable, and if object A and object B were sitting on this record, object A would go around 360 degrees in the same amount of time as object B would go around 360 degrees. So they have the same rotational speed. However, we see the point further away from the center, that would be point B, travels a longer path, or what we call circumference. So it does so in the same amount of time, though. And therefore, as we get further from the center, part B has a greater linear speed because it goes a larger circumference in the same amount of time. And what I want you to do here is you can pause the video and try and answer these questions, and then you can unpause and see how well you did. We again see that we have these two ladybugs, Ladybug A and Ladybug B. What will be the same about Ladybug A and Ladybug B? And which one will be different? So your options are linear speed or rotational speed. Which one will be the same and which one will be different? So go ahead and pause the video, and when you're ready, you can unpause and see how you did. All right, welcome back. Ladybug A and Ladybug B have the same rotational speed because they both will go through 360 degrees in the same amount of time. However, Ladybug A and Ladybug B have different linear speeds. Ladybug B goes a further distance than Ladybug A, and so therefore, because they go different distances in the same amount of time, their linear speeds will be different. Now that we know that they have different linear speeds, I want you to tell me which ladybug, A or B, will have a greater linear speed and why. Go ahead and pause the video. When you're done, go ahead and unpause and see how well you did. Welcome back. So which ladybug has the greater linear speed? Well, we see here that Ladybug B has a greater linear speed because this one goes a further distance in the same amount of time. And the reason is, again, Ladybug on the outside travels a larger distance in the same amount of time and therefore has a greater linear speed. Just like those students running in the circle doing the whip. The student on the outside had to run faster than the student on the inside. And that's because they had to travel a further distance. Now the last thing I want you to do is we have two different equations for speed based on if it's linear or if it's rotational speed. The equation on the left, we have that S is the speed, just like we've done before, measured in meters per second. Sometimes in this class we'll also measure in meters per minute, but usually we'll be measuring in meters per second. D is the distance, and that's measured in meters. And T is the time, and that's measured in usually seconds or possibly minutes. The equation for a rotational speed, we have this funny looking symbol here. It almost looks like a W, but it's not. It's actually a Greek letter, omega. And omega represents the rotational speed. It could be measured in either revolutions per second or rotations per second, or revolutions per minute, or rotations per minute. A lot of times we abbreviate these as RPS for revolutions per second, or RPMs as revolutions per minute. If you know anything about records, long playing records are measured in 33 1/3 revolutions per minute, whereas the singles are called 45s because they are spinning at 45 revolutions per minute or 45 RPMs. Of course, we have the revolutions up here, and T is representing time, which is measured in either seconds or minutes.